Okay, today we're going to learn about Ohm's law. Okay, so what is Ohm's law actually? It says that the Ohm's law says that potential difference across a metallic conductor is directly proportional to the current flowing through if its temperature is constant. So it's a law. It's law that it says that if we have temperature is constant, okay, the potential difference PV, potential difference PD, sorry, across a conductor will be directly proportional to the current flowing through its temperature is constant. Okay, so mathematically, it says V is directly proportional to I when the T is constant. Then V will be equal to IR. Okay, so V so it says that the Ohm's law can be stated in the terms of electric field and current density. So now we're going to derive. We can say that derive a J equals to sigma E. This is equal to V equals to IR. So we consider first a uniform conductor of length L and cross-sectional area as shown in figure below. So we have a conductor. It's a metallic conductor. We have a cross-sectional area, and we have a I that is flowing from left to right, and E also flowing left to right. Okay, so we have to also consider that where is a proton. Okay, a proton move in the opposite direction of current, so E, we assume that positive to negative side, so E is correct, left to right, but electrons are moving towards the positive side. Okay, from low what I call that, high potential to low potential. Okay. Next, potential difference V is maintained across the conductor set up as an electric field E, and this field produces a current I that is proportional to the potential difference. If the field is assumed to be uniform, the potential difference V is related to the field through the relationship below. So V equals ED. Okay, this is a equation that we have learned before, and V equals CL actually is just a numeric configuration of D and L. Both are in the length of the conductor. From the Ohm's law, V equals IR, where I equals to JA. Remember, from here, J equals to I over A, current density, and R equals to, this is resistance equals to resistivity. Okay, times L, the length, divided by the cross-sectional area. So EL equals to JA over PL over A. Okay, so E equals to rho J, and rho, this is resistivity, and this is conductivity. Okay, or we can say that J equals to sigma E. So J equals to sigma E is actually equivalent. Is equivalent to V equals to IR. Okay. So you can see that from V equals to IR, V equals to J equals to sigma E. Okay. So it's equivalent. So we have a figures here, figures 18.6a, 18.6b, 18.6c, and show the potential difference against graph of various materials. So we have a metal. Metal is a ohmic conductor. Okay, because why we call ohmic? Because it is obeys a Ohm's law. So you can see that 0 to E is directly proportional. Okay, with the gradient M. For semiconductor, it is not actually a ohmic conductor. So you can see that the loss of V is a proportional to I is not cannot be used in this situation. So semiconductor is not a ohmic conductor. We call as non-ohmic conductor. For carbon, carbon also is not an ohmic conductor. You can see that it is a inverse of V over I. Okay, and electrolyte also is not an ohmic conductor. Okay. So depends. Some conductor has resistance which depends on the current flowing through a known as ohmic conductor. As I said, is obey to the Ohm's law. Meanwhile, non-ohmic conductor are conductor where the resistance depend only on the temperature. Okay. So we have an example here. A copper wire carries out a current of 10.0 ampere. The cross-sectional of the wire is a square of side 2.0 mm and its length is 50 meter. The density of the free electrons in the wire is 8.0 times 10 power 28 meter cube. Determine 1. The current density. B. The drift velocity of the electrons. C. The electric field intensity between the both ends of the wire. D. The potential difference across the wire. And the resistance of the wire. I can say that number 1 is asking for current density divided by J. The drift velocity is Vd. Electric potential field intensity between both ends of the wire. So this is E. Potential difference across the wire PV. PD. Potential difference. The resistance of wire uh, is R. Okay, resistance of the wire. So given that the resistivity of copper is 1.68 times 10 negative meter, so this is the rho, and the charge of electron is 1.60 times 10 power of negative 9 coulomb. So solution is, first we have to list out all of the variables there. A, the current density is given by J equals to I over A. So we can have here I is given and A is also given, okay, with a square of side 2.0 meter mm. Okay, so A over here is A squared because it is a wire square of side. Okay, so J equals I over A square. So we have 2.5 times 10 power 6 ampere per meter squared. Okay, now number 2, the drift velocity of the electron Vd. Okay, by using equation of drift velocity, thus Vd equals I equals Navi. I equals an AEV, or I equals to Navi and A VDE Navi. Okay, and A equals to A squared for the cross-sectional area. Vd equals to I over an AE. So Vd equals to 1.95 times 10 power negative 4 meter per second. Okay, so it's actually very, very slow. Electric field intensity is E equals to rho J. Okay, so E equals to rho, that is the resistivity times the current density J. So E equals to 0.042 Newton per coulomb. Okay. Next, by applying the relationship between uniform E and V, hence V equals to EL. Okay, so V equals to EL, that is E is taken from the question before, the answer from question before, 0.042. So 0.042 times 50, L is the distance. Okay, so V equals to 2.1 volt. On the Ohm's law, therefore, V equals to IR 2.1 equals to 10.0 R. So resistance is 0.21 ohm. Okay. So this question that I give you, okay, you can pause the video, okay, take your time and do all of the question, okay, and then you can check the answer with the red writings on the bottom. Okay, so for A, for instance, okay, the current in the block is 0.83 times 10 power negative 2 ampere. the current density in the block. Okay, that is J over here is 109 ampere per meter squared. The real velocity of the electron Vd, okay, that is 1.28 times 10 power negative 2 meter per second, and magnitude of the electric field in the block is 2.27 meter per volt per meter. Okay, so this one you can pause. Okay, this video you pause and then you can do by your own. You can check the answer. Any problems solving the question, you can ask me into the WhatsApp. Okay, group. Okay, this is a question number 2. We have two rods made from two materials. Each conductor has a square cross sectional and 3.00 millimeter on the side. The first material has sensitivity of 4.00 times 10 power negative 3 ohm per meter and is a 2.25.0 centimeter long, while the second material has sensitivity of 6.0 times 10 power negative 3 ohm meter and is a 40.0 centimeter long. Determine the resistance between the ends of the rod. Okay, so actually you have two kinds of resistivity. One over here, resistivity is rho. Okay, is 4.00 times 10 power negative 3 ohm meter. And over here we have resistivity rho equals to 6.00 times 10 power negative 3 ohm per meter. Okay, so you have two kinds of material with different resistivity with two different length over here. Then it was attached. Okay, it was in the contact of one of its side. Okay, so determine the resistance. What will be the resistance of the whole thing? So actually, basically it's a resistor that is combined in the series. Okay, you can see that this is number 1 and number 2. It's a resistor combined series. So you have remember ID is a parallel. What is a formula for parallel resistor? And what is the formula for resistor are connected in series? So you can get the answer that is 3.78 ohm. Okay, you can pause this video and then you can do by yourself. Okay, I'm going to continue to the next question. Okay, so number 3 is a 2.0 meter length of wire is made by welding end of the 120 centimeter long silver wire at the end of 30 centimeter copper wire. Each piece of wire is 0.60 mm in diameter. The potential difference of 5 volt is maintained between the ends of the 2.0 meter composite wire. So determine A, the current in the copper and the silver wire. B, the magnitude of electric wire in copper and silver wire. C, the potential difference between the ends of the silver section of the wire. Okay, so you have actually a similar question to number 2. Okay, but there are 3 question. Okay, 3 different questions that asking for one current, B is electric field, okay, and C is a potential difference. Okay, so answer over here, you can pause the video and you can do by yourself. Okay, okay, now we have a second part is electrical conductivity and resistivity dependence on resistivity of the temperature. So by Ohm's law, just now we know that when we have a condition of temperature that is constant throughout the procedure of the experiment, okay, the V will be is directly proportional to I. Okay, but if we have a temperature that is increased or decreased, okay, there will be a difference of resistivity to the material. Okay, we're going to find out in microscopically what happened to the atoms inside the conductor. One is when we have a metal over here. Okay, we have a metal standard conductor. The resistivity of metal increase with an increased temperature. At low temperature, 0 to 373 Kelvin, the resistivity change linear with the absolute temperature. At high temperature, the resistivity is no longer change linearly to the absolute temperature. Okay, so remember when we learn about uh, drift velocity, okay, there will a lattice atom that is vibrate up and down. Okay, so this lattice atom, okay, it depends on the temperature outside of the conductor. If we heat up the temperature of the conductor, we heat up the temperature. Where is it? My mouse. Okay. We heat up the temperature of the conductor. What happens is the vibration will be, the amplitude of the vibration will be bigger. So it will be bigger and bigger. What happens is the free electrons, okay, I call as a free electron is hardly to pass through from one side to another side. You increase more the temperature, the vibration of the lattice atom will be bigger, and the more uh, the smaller of amount of free electron can pass through from left to right because the amplitude is higher and higher and higher. Okay, so for a metal, the higher the temperature, for a metal, the higher the temperature, T increase, R also increase. For semiconductor, the resistivity of semiconductor over here, number 2, okay, the decrease with an increase in temperature. At low temperature, the semiconductor usually have high resistivity. This is because low temperature there are no many charge carriers that can move freely. As the temperature increases, the resistivity of the semiconductor decreases. This is small charged particles have enough energy to become free charge carriers. The number of free charge therefore increase. Semiconductor has a different concept from a metal. Semiconductor, each of the we call as the atoms has a extra, either it has extra or it has a hole over here. Each of the atoms ion, it has an extra electron out of the uh, the the furthest orbit. Okay, so when you increase the temperature, when you heat up the temperature of the semiconductor, what happens is there are more electron over here. They are free. It is free because they are not bound anymore to the nucleus itself. So when you increase the temperature, the resistivity will be lower. It's because you make more free electrons as you increase the temperature. Okay. So by semiconductor, it is better if the temperature is higher. More free electrons are, uh, released from the atom, from the electron. Sorry, from the orbits of the atom. So now we have one more. It's a sulfur conductivity. Okay, resistivity of the conductor is a temperature dependent. In increase of temperature increase, resistivity of conductor and vice versa. Okay. So if the temperature of the conductor decrease to absolute zero, the vibration of atom decreases. Okay. So the lattice atom, as we learned before, will be decreases until there are no amplitude. Okay. There are no vibration. And might consider stationary, so we can call it as stationary. The conductor will have zero resistivity. There are no blocking of the free electron. Such conductor have zero resistivity, also called a superconductor. This is why we call it a superconductor. Yes, we found especially that some material behave superconductivity at 77 Kelvin. Okay. So when some materials have we cool it down, cool it down to 77 Kelvin. Okay, there are no more resistance on that material. Okay, uh, so let's say over here, okay, this is a G stands for mercury. Okay, so when mercury is cooled down to where here we have a 4.2. Okay, from this is cool down to the lower part until 4.2 Kelvin. Okay, it drops down dramatically. You can see that it drops. It was not more linear. It drops down dramatically. So over here is between 4.2 and 4.1. 4.1 is already called as critical temperature. You see here, TC, critical temperature, critical temperature. This is when the resistance 0.00. The resistance is already 0. Okay, so it's dropped to 0. So there are so many applications when we have a superconductor, but remember to cool it up, to cool it down. Okay, you need a lot of energy. Okay, uh, so once a current is set up in the superconductor, it persists without any applied voltage. Okay, so actually it's saying that if you have a battery, okay, you have a battery over here, and then you have a current flowing in the in the circuit. Okay, when you cool it down to critical temperature, this material, I mean the wire over here, okay, you take out the battery, the current will be still flowing inside the circuit. Okay, without the battery itself there. Okay, so this is uh, what happened when you have a superconductor there. Okay, effect of temperature on system, metal. Okay, so we make a summary again. When the temperature increase, number of free electrons per unit metal remain unchanged. Okay, metal atom is structural like this, vibrate with greater amplitude and cause the number of collision between the free electrons and metal atom increase. Hence, the resistance in the metal increases. For superconductor is a class of metal and compound whose resistance decreases to zero when they are below the critical temperature Tc. Okay. So this is a critical temperature for various superconductor. Okay. So all units over here are in Kelvin. Okay. When the temperature of the metal decreases, its resistance decreases to zero at critical temperature. Superconductor may have technological applications such as 1. Magnetic resonance imaging, MRI, okay, magnetic levitation of the train, and faster computation, okay, and powerful electric motors, and etc. Okay, so remember, if you remember before, the resistance of the electricity is the one who make up the heat. Okay, so efficiency will be decreased because the energy, some of the energy are converted to heat. So if we have a superconductor, okay, uh, there are uh, the converted energy that is transferred to heat will be decreased. So we have a more efficiency of the machine or electronics. Okay, so I'm going to stop here. Okay, and I'm going to give you some tutorial. I mean the question is tutorial, and you do it yourself, and uh, you have to pass up in the Google Classroom. Okay, the answer of the tutorial. So I stop here. Okay, see you tomorrow. Thank you.